So yesterday we were talking about this Ferris wheel, and we admittedly said that it was going kind of fast, which makes it rather fun. So we want to figure out now if you were to draw this Ferris wheel. Okay, here's kind of the 5 feet above ground. There's the Ferris wheel. We'll set it right there. We'll make it a little bit bigger right there. Okay, here is the radius. And so if you're a rider right here, let's say here's the chair, and you're sitting in the chair right there, right? You're sitting in the chair. There's your legs. Your arms are up because you're having a good time. And then you're like, woo, right? You're going through the air. We want to figure out how fast you're actually moving through space. That's your linear velocity. Now, we call it linear velocity, like we did in the section when we studied it, but it's around a curve, yes? So it's also called the tangential velocity. So if he were to fly off of that seat and go in a straight line, that would be the same speed that he's traveling around the curve. The nice thing about linear velocity is when you go fast enough, it blows your hair and you can feel the breeze and you're like, yeah, this is fun. But it's even more exciting when you experience it around a curve because now you feel the G-forces pushing you to the outside. So it's an extra thrill. Well, we want to figure out what that is. So y'all remember the formula for linear velocity in terms of angular velocity? That's how you find omega, theta over t. But I want to know what linear velocity is. V equals R times omega. Yeah, it's real easy to remember if you just remember omega is your angular velocity, and then your speed around the curve is directly proportional to your radius. The farther you are from the center, the faster you have to go to make one rotation because your circumference is bigger. So V equals R omega. So I think we have both of these. What is our radius of the Ferris wheel from yesterday? Do you remember? 55 or 50? I think it was 50. Yeah, 50 feet. I'm going to go ahead and put units in there, 50 feet. And what was our omega? How fast did it rotate? Did they tell us that? 1 revolution every 10 seconds. Remember, that's not the angular velocity. That is the frequency. That's the period. That's the reciprocal of the angular velocity. So we want either 10 seconds per one rotation, or we can even use what they gave us, 6 RPMs. Remember that? It doesn't matter. We could say that the angular velocity is either 6 RPMs, or we could say it's 1/10 of a rotation per second, RPS. It doesn't really matter. I'm going to use 6 RPMs just because it's not a fraction. So we'll do 6, and I'll do revolutions per 1 minute. I'm going to write it like that. Now it does say to find it in miles per hour. We have a much better appreciation for miles per hour than we even have for feet per second. So what do I have to do now to convert from feet revolutions minutes to miles hours? Yeah, I got to do some stoichiometry, right? I got to do some dimensional analysis, some conversion. So let's get rid of the feet first. I'll say feet in the bottom, and I'll put miles in the top. And of course, we know 1 mile is how many feet? 5280. Everyone remembers that, 52 meto. And then that gets rid of the feet. And then we'll have to get rid of the revolutions, don't we? 1 revolution is 2 pi radians. Or we don't even need to put rads, do we? Not anymore. We understand that it's unitless. And now we need to get from minutes to hours, right? So we need to get minutes on the top, hours in the bottom, and we know that 1 hour is 60 minutes. And now we know the minutes divide out, and if we take inventory of our units, we have miles on the top and hours on the bottom. Is that what we want? Yeah, so let's see. Now I go to my handy-dandy calculator from the state of Minnesota. Takes a while to load. Y'all can do it faster than I. So maybe someone can even tell me. I don't even have to type it in. Yeah, I'll just. That's kind of slow, right? It's 50 times 6 divided by 5280 times 2 times pi times 60. 21 point what? 419. That's a little more reasonable. So as fast as this thing is rotating, we're still only going 21.419 miles per hour. So you can imagine how that would, I mean, if you've ever driven through Landa Park at the speed limit, it's 20 miles per hour. If you've ever had the windows down, you stuck your head out like a dog. No one's ever done that. How about riding in the back of a pickup truck? That's not really legal much anymore, right? Back in the day, you used to throw like 15 kids in the back, and they would sit on the top rail instead of in the bed, and then just be hitting the bump. Whoa! Johnny almost died, right?
Yeah.
Yeah, don't really do that anymore. But that would be 20 miles per hour. That's kind of how fast you're moving through air. That's a pretty good clip, right?
We still do that.
You still, yeah, I know. I don't think it's legal anymore, though, is it?
Oh.
If cops catch you, they probably don't ticket you. They just say, "Do you have a death wish, son?"
You have to be 18.
Oh, and if you're 18, you can.
Yeah.
It's funny because I was driving on the highway a couple of weeks ago, and I actually saw one dude in the back of a truck on the highway, and you just don't see that anymore. And he was like staring at all the people that were coming up behind him, and his hair was blowing, and he's not making eye contact. He's just kind of awkwardly looking down. He's like, "Yeah, I'm sitting in the back of a truck going 80 miles an hour," and it's just like, what does it say?
Texas law permits adults 18 years and older to ride in the open bed of a truck or open trailer.
Okay, so it is legal if you're 18. You just don't see it much anymore.
Yeah, but even if you do and you get caught, the fine's only $25 to $200.
Oh, yeah, kind of slap on the wrist. Yeah. Well, it was commonplace back in the day. I mean, that's why everyone wanted a truck. It's just a people hauler. Okay, and it is safer to sit with your butt on the bottom of the bed instead of up on the rail. Yeah. Okay. Any questions about that example? Because we're going to modify it now. Earbuds out, phones away. Yep. All right, round 2. If the rider from example 1, you remember that guy? That's this guy right here. If that rider right there from example 1 started his stopwatch, not when he was at the bottom when the ride started, when he was 5 feet above ground, he was a little slow on starting his stopwatch. He started it when he was 12 feet up in the air going up. What would the new equation of his height above ground be as a function of time? So 12 feet. So let's think about it. 12 feet is going to be somewhere right about here. Okay, there's 12 feet. That's when he started his stopwatch. So what we need to do is we need to figure out how much time elapsed between when he started at the bottom and when he was 12 feet in the air going up. Would you agree? And then what I need to do is I need to make that point my new y-axis. I need to shift this graph over to the left, whatever that amount is, so that that's my new y-intercept. Okay? So how can I figure out the time where it was 12? Well, all I got to do is take my original equation from part A. Let's do it down here in part B. I'll take my original equation, and I'll set it equal to 12. Now, I do need to pull up my calculator for this. Let's see if it loads. There it is. And you probably have to type in your equation again from yesterday because we didn't get to finish, but that's okay. It's not that bad. You should be in radian mode. I don't think anyone changed it, but it's worth a check. Negative 50 cosine of pi fifths t plus 55. Minnesota's having bandwidth problems this morning, or maybe it's our end. I don't know. I'll blame Minnesota. Maybe the mosquitoes are attacking. The state bird of Minnesota, they say, is the mosquito. Come on, loading. Please wait. It's so polite. Please wait. Please, pretty please. All right, so I'm going to go back to y equals negative 50 cosine of parentheses pi divided by 5 x close parentheses plus 55. And then I go back to my window, and I'm going to go from 0 to 30. I'm going to count by whatever, 2.5 or 0. I'm going to go from negative 10 to 115, and I'll just graph it. Okay, there it is. It looks good. Now in Y2, I'll come back and graph 12. Now remember, we have to look for the right point of intersection because it intersects many, many times. He started his stopwatch when he was 12 feet in the air going what? Up or down? Up. And we can assume, it doesn't say for the first time. He didn't wait till he was all the way around. So he started it right there. But he could have started it on the way back down, but he started it right there. So I need to figure out that first point of intersection. So once we have it graphed, how do we find it? Second trace number. Yeah, go to the calculate menu, second trace number 5. enter, enter, and then we just scroll over towards it. Enter, enter, and we scroll over to it. And it tells us that t is equal to 0.852. I'm going to go ahead and store that as a. I don't know why, but I just think I might need it again. So I'm going to go to the home screen, and I'm going to store it. I'll have to do x first. X stow alpha a. And there it is. All right, so now I need to modify it. Let's call the new one capital H. How about that? So we don't get confused with little h. Capital H of t now, because he was a little bit late. Is the amplitude still going to be 50? Negative 50 for the a value? Yeah, it actually will be. Nothing changes except the phase shift. We're going to take this graph that has that equation, and we're just going to shift it to the left by 0.852. That's it. Nothing else changes. So we can still use negative 50. We can still use cosine. It's going to be pi fifths, but now we're going to have parentheses t plus or minus something plus 5.5. And of course, that value is going to be 0.852. My question to you is, though, is it plus or minus? Minus would shift the graph to the what? To the right. Do we want to shift this graph to the right? We want to pick this graph up and move it to the right? No, if I move it to the right, I'm going to get this piece over here on the left, and that's going to be 12 feet going down. I want to pick this graph up and move it to the left. I want to physically move that graph over to the left. So if we're moving it to the left, it should be what? Plus. Now, if you're not sure, you got your calculator, come back over here and just try it out. Do parentheses, and I'm going to do x. I'm going to try minus, and because I stored it as alpha a, look what I could do. Because I stored it as alpha a, I'm going to get a more exact answer, and I don't have to work as hard to type it in. I don't have to put 0.852. I just put a. If you hit graph, you can see it. It starts at 12. It now starts at 12, but it's 12 doing what? Going down. That's not what we want. We want 12 going up. So you could say, it's not going to be minus. It must be plus. We have to move it. So remember, it's the opposite of what it appears. Is that 12 feet going up now? Yeah, you can even verify by hitting trace. We're on the blue curve. Hit 0, and you can now see that we're at 12 feet. It's going up. So not a big deal, right? You're going to have new critical values. We're not going to mark those. We're not going to graph it. We're just going to modify the equation to get the new equation. Okay? And that's it. That's it. So whenever you're doing your own experiment, it's always better if you time it correctly. Hit start as soon as the experiment begins. Otherwise, you're going to have a funky phase shift, and your critical values are going to be funky numbers, and it's better to just be on cue. All right? Okay. It's the same graph, it's just shifted, a phase shift. That's all. It's just a little bit out of phase with the original one. All right, that concludes example 2. Let's kind of shift gears here to a different scenario. No more Ferris wheels. This is kind of like a science experiment, and this is where you neglect gravity and air resistance and all this good stuff. It's an ideal situation. We've got a weight that is hanging from a spring attached to something at the top, okay? We are going to begin this weight into motion by either stretching it and letting it go or compressing it and letting it go. It'll say which one. And then the idea is once it starts oscillating from the spring, it's going to go down to a low point of 40 centimeters above the ground when it's extended its full length. And then as it recoils and compresses, it's going to get to a high point of 60 centimeters above the ground. And if we neglect gravity and we neglect air resistance and all those other things that's going to slow it down, we can assume that it's going to be a perpetual motion machine, right? That's the safest assumption. It's going to perpetually just go up and down between 40 and 60, 40 and 60, 40 and 60, 40 and 60. Now, that's not what is actually going to happen, but that is the ideal scenario. And that would also be simple harmonic motion. So we want to model that, all right? Now, to make it kind of more exciting, I say the rider from example 1 and 2 leaves the fair, and he goes home, and he constructs this perpetual motion machine. So the rider sets the spring in motion. There it is. The rider sets the spring in motion by compressing it to a high point of 60 centimeters above the floor. So we're starting it by compressing it. at which time he starts his stopwatch. Okay, so he's timing it perfectly. He's going to push it up to the high point of 60 centimeters, compressing the spring. He's going to let go as soon as he hits start on the stopwatch, so that's 0. Now, it tells us a little bit of information. 1.8 seconds later, it gets closest to the floor at 40 centimeters. Okay, sketch the graph of the sinusoidal motion. Okay, so here we go. We got a y-axis, we got an x-axis, and we're measuring the height above floor. Now, it doesn't tell us the variables to use in this problem like it did in the previous problem. It doesn't say use h of t, but since we are measuring the height above the ground, h of t would be another good variable to use. So I'm going to use h of t again, but this time it's in centimeters above ground. And then over here, I'm going to use t again for time, and we're talking about seconds. So that's the same. All right, the y-axis is usually the easier of the two to set up. I can come over here. We could do like a little break in the graph if you want. I'm going to call this 40, and I'm going to call this 60. Okay, and then I'm going to bisect it and find the midpoint. What's the midpoint of 60 and 40? 50. And that should be my what? That should be my sinusoidal axis. So I'm going to go ahead and draw a dotted line through 50, just like that. Perfect. Now I do want to start collecting my information. So over here on the left-hand side, we'll do A, B, C, D, P, and R. We already know the range. The range is going to be all the heights that are between 40 and 60 centimeters. So we can write that down. We know the D value is 50. We got that. The C value we always wait on. Do we know the amplitude? Yeah, what is it? 10. It's the distance from 50 to 60 or 40 to 50. Yeah, it's 10. And again, all we have left to do is find B and P. Well, we get the P from the graph and we convert it. B is 2 pi over P. So we just need to find P. Well, to find P, we need to sketch the graph. So here we go. We are starting it at T equals 0 by compressing it. So notice we have a critical value at 0 again, don't we? It's a high point this time instead of a low point. So that could be a what function without a phase shift? Cosine. Cosine starts high. Yeah. Now I need some, it doesn't tell me the period, it doesn't tell me the angular velocity like the Ferris wheel, but it does tell me that at 1.8 seconds, it's at a low point. So I'm going to come out here a little bit further, and I'm going to call this distance, whatever, it's arbitrary, but I'm going to call it 1.8. And that's going to be my first low point. What fraction of a cycle is that? From a high to a low? That's a half a cycle. So I'm going to come down here, and I'm going to say 1/2 of the period is 1.8, which means the period is what? 3.6. There you go. And of course, 1/4 of the period, which is really what we want, is going to be half of 1.8, which is what? 0.9. Okay, cool. So that's enough to get my marks. If I bisect this distance here, I can call that 0.9. And that's my most important value on this entire graph. So now I can just add the rest of the marks, and I'm keeping this distance right here between 0 and 0.9. Again, I'm just eyeballing it. I don't need a negative one here because, again, he started it at 0. So I'm just eyeballing it, putting down a few marks until I run out of space. Whatever. That looks like enough. And then we just keep marking them by adding 0.9. So 1.8 plus 0.9 is 2.7, 3.6, 4.5, 5.4, 6.3, so on and so forth. The y-axis is the y-axis. It didn't move. Okay, he was smart enough to start his stopwatch at the beginning. So now I can just put the food on the table. There's an axis, there's a low, there's an axis, there's a high, there's an axis, there's a low, there's an axis. Looks good to me. And now I connect these with nice quarter cycle arcs. exaggerating the inflection value on the axis points, turning the corner when I need to, and there you go. That's the simple harmonic motion of the spring above and below the floor. All right, now let's write an equation. So h of t is going to be, again, if we don't want a phase shift, which is the most ideal one, it starts at 0 at a high point, so that would be a what? What do we say? If it starts at a high point, cosine, so the amplitude is 10, so it's positive 10 cosine of b. We haven't found b yet, have we? It's 2 pi over p, so that's 2 pi over 3.6, which should be pi over what? 1.8? Now, here's the deal. I won't allow you to put pi over 1.8 if you want to get credit for it. Okay? Why won't I allow pi over 1.8? Because it's mixed notation. You have a fraction, which is used to represent parts of things, and you have a decimal, which is used to represent parts of things. So that's kind of like talking Spanglish to somebody, broke in Spanish and English mixed. I want you to write it as a rational number. So let's come off to the side here, and let's think of 1.8. What is 1.8 as a fraction? Well, that's the same as 1 and 8/10, isn't it? That's how you read it, 1 and 8/10, which you know you convert that by multiplying 10 plus 8, you get 18/10, which simplifies to 9/5. Now you might just know that 1.8 is 9/5. Okay, but if not, you can convert it. 1 and 8/10, 18/10, simplify. Okay, so now if we have pi divided by 9/5, that's the same as pi times the reciprocal, 5/9. Yes, yes? So if I put the pi over 1 and I multiply straight across, I get 5 pi ninths. And that's a much better looking value of b. Okay? So pi over 1.8 is not incorrect. It's just ugly, and I won't accept it as an answer. And I won't have it as an answer either as a multiple choice question. So 5 pi ninths. And then I can just put t instead of x. There's no phase shift. And then, of course, I need my plus 50 to get it up to the midpoint there. There's your equation. All right, so that we answered part A, and we just answered part B. This is part B. The equation is part B. The graph is part A. All right, once we have the equation, it's time to graph it on our calculator so we can start answering questions. So I'm going to go ahead and delete that if I can, if it'll let me. There we go. And I'm going to type in Y1. It won't let me get to Y1. It's skipping Y1 for some reason. Let me try it again. There it is. All right, so we get 10 cosine of alpha x, 5 pi divided by 9, x, we use x instead of t, plus 50. And then again, we don't hit graph. We work so hard to get this beautiful graph in this nice window. We go to the window and it looks like I'm going from 0 to 6.3. So you can go out as far as you want. I'm going to turn my x scale to 0. We really don't need it. We don't really need it. And then my y min, I like negative 10. That's 10 below, bless you. And then I'm going to go to 70, which is 10 above. Bless you. And then I'm going to turn my y scale also to 0. I just turn x scale and y scale both to 0. And that's as far as we need to go. We don't need to worry about the resolution or the change in x or the step or anything. All right, now I hit graph, and you should see something similar to what we sketched. Theirs is a little bit higher on the graph because I have these two lines right here means that it's a broken graph. Like we took the top part and we brought it down towards the x-axis, so we wouldn't have to go so high into space. Did you eat a Carolina Reaper? No? Okay. Does that look right? That looks like ours, right? So now we can answer questions. Part C. Here we go, part C. What is the distance from the floor when the stopwatch reads 10.5? At this time, is the weight moving away from the floor or towards the floor? Now, my window went out to 6.3. It didn't go out to 10.5, did it? So, again, you have two options. You can change your window to an X max that includes 10.5, or you could just do it the way we did yesterday, which is what I'm going to do. Now, first, you have to put H of 10.5. If you don't show that, you're not going to get credit for the answer. So I'm going to go to the home screen now. Alpha trace number 1 of 10.5. It gives us 58.660 centimeters. So there's your numeric answer. All right, there's your numeric answer. There's a check for having both sides of the equation. All right, now I want to know if it's going up or down. So let's go the same thing, alpha trace number 1, and I'm going to go of 10.5 what? 10.51. Let's look a hundredth of a second later. What did it do? It's going up, right? Okay, so now I'm going to write the sentence. So we're going to say at 10.5 seconds, there's the first part of the equation with units, or the sentence with units. Okay, the weight is 58.660 centimeters above ground, or above the floor, whatever you want to say. Above ground is fine. Moving up or upward, I don't care. Moving up. I'm going to write upward, or towards the heavens, if you will. It's moving towards the heavens, towards the ceiling. It's raising the roof. Whoop, whoop. We have units on both of them. There you go. Remember, you don't need units over here. You don't need units on your independent variable when you're doing the numeric answer. But in your sentence, you need the units on both of them. Okay? So that would be another check. All right, so that's part C. Any questions so far? Yeah, the fun part's kind of done. The fun part is deciphering the information, making the pretty graph, writing the equation, and then it's just kind of like, oh, we're just using an equation. It's kind of boring. But that's why we do it, so we can predict. Part D, what is the first positive value of time when the weight is 47 centimeters above the floor? What is the first positive time where it's 47 above the floor? Does it matter if it's going up or down? Not in this case. So I'm going to say h of t equals 47. There's the check right there. And then I go to my y equals, come down to y2, type in 47, hit graph, and I'm looking for the first point of intersection. Doesn't matter if it's going up or down. It happens to be going down. Second trace, number 5, enter, enter, scroll to the one we want, hit enter, and there it is. T equals 1.074 or 5, and that's our final numeric answer, so we put units on it. You don't have to write the sentence here, but if it asks for the sentence, you would include both units. All right, so that's D. Now we're on E. During the first 9 seconds, oh, here's one of those duration ones. During the first 9 seconds, for how long is the weight 53 centimeters above the floor? So kind of like what we did yesterday. So I'll accept this. Either h of t equals 53, or what's really happening is h of t is greater than 53. Well, either one of those I'm fine with. Okay, so now we go back to y equals, instead of 47, we do 53. Now, because it tells us during the first 9 seconds, I am going to go to my window, and I'm going to change my x max to, guess what? I'm not going to change it to 10, actually. I'm going to change it to 9. I'm going to go straight from 0 to 9. I want to see only the situation on the screen that we're talking about. Okay, so here's what I noticed about it. I noticed that it starts above, what did I say? It starts above 53 for a little bit of time. So I got to find that first point of intersection, yes? Because that's the first amount of time that it's above 53. But then there's 2 complete cycles where it's above 53. Yes, yes? So all I got to do is find the difference of one of those to the next one, the points of intersection, where it goes up and comes down, subtract them to find the difference, and then double it, right? Because of the symmetry. So that's my plan. So here we go. We're going to find 3 points of intersection. So the first one is going to be the first one that we see. Second trace, number 5, enter, enter, and I'm going to scroll over to it, enter. All right, so that's 0.725 seconds. I want you to report it, but now I'm going to store it as A, and I'm going to call it A on my paper. So remember to store it. Go second mode, that's quitting, and then just hit X stow alpha A. Boom. And now it's in there. Questions on how to store a value? Second mode quits to get you to your home screen, and then you hit X stow to the letter 1, alpha A. Everyone good? If you're off in the third decimal, it's wrong, and all your work is for naught. All right, let's find the second one. I'll call it T sub 2. Second trace number 5. Enter, enter, and this time it doesn't matter which cycle I use. I'm just going to use the first one because it shows up first and the numbers are smaller. I'm going to hit enter there, and I get 2.874 seconds, and I'm going to store that as B. So I'll call it B on my paper, and I'm going to hit now X stow alpha B. Boom. So notice it overwrote whatever X was, but at least I stored it as A before I did that. And then I got one more, T sub 3. Second trace number 5, enter, enter. This time I want the next one right there. Boom. Okay. And it gives me 4.325 seconds. I'm going to store that as alpha C. So I come back and I hit X stow alpha C. So now I got all three of them. If you want, you could find the next two as well and call it D and E. But I know that it's symmetrical to the first little bump, and I can just double it. So here's the work that leads to the answer. So the weight is above 53 centimeters during the first 9 seconds. And then we show the work that leads to our answer. It's going to be A plus 2 times C minus B. Are you okay with that? A is the first amount that we started with up to the first point of intersection. C minus B is the duration of the first bump. And then we double it because there's a whole nother bump. Got it? Now all I got to do to figure out what that number is guess what? Type that in to the home screen. Alpha A plus 2 times parentheses alpha C minus alpha B. And now you know that you're going to get the right answer and there's no intermediate rounding error. 3.627 seconds. Okay, so for this one, you're going to get 1 for the method. You're going to get 1 for showing the method, and then you're going to get 1 for the answer with units.
You also do the initial 1 times 5.
Well, if you do the initial 1 times 5, you're assuming that it's symmetrical, right? You're assuming that it's symmetrical. This doesn't this first one right here doesn't necessarily happen. Okay, in general, this first one right here doesn't necessarily happen. It is a high point, right? But if this were shifted a little bit to the left or a little bit to the right, then that wouldn't necessarily be a fourth of everything or half of one of these. But yeah, if you know you're starting at a high point, then you could find this first one here and know that you have 1, 2, 3, 4, 5 of those. So you could do 5 times the original. But that doesn't work in general. But you can certainly do it here because we start at a high point. The high point is 0, which is a critical value. So that would work also. Yeah.
Whenever there's no C or
Right. If there's no C, if there's no phase shift, and we're about to do a phase shift, so you just got to be careful. If it looks like it's half of what the other two bumps are, it doesn't always mean that it's half. But in this case, it is. So I would also accept to do it. Lawson said we could also do or 5A, right? Let's see what 5A would give us. It should give us the same answer here. 5 alpha A. Yeah, it gives us the same answer. Equals 3.627. And then you would get to check for that. So as long as you're showing your work and you're getting the right answer, I don't really mind how you do it. But I need to be able to see how you arrived, bless you, at your answer. Okay? 5A is enough of an indicator of what you're doing. All right. Any other comments or questions before we move on to his little sister getting in the project? Yeah, I know, right? So here we go. The last part here, part F. What if the writer's little sister comes in and starts the machine while the writer is still at the yogurt shop? He stopped at the yogurt shop after the Comal County Fair. She started the perpetual motion machine for him. She was supposed to wait for him, and she was only supposed to witness it. He was supposed to start it by compress, but she got too excited. She was too curious. So she started it, and we don't know how she started it. She could have compressed it, or she could have pulled it, but once he got home, it was already in motion, okay? And he tried to time it. He didn't want to stop it and restart it because it's perpetual, right? You're messing with black holes if you do that. So he just started his stopwatch at an arbitrary time. Okay, and this example says, what now if he started his stopwatch when the weight was 51 centimeters above the floor, moving away from it? What would the new equation be? Well, it's kind of what we did on the previous problem. We're going to have to say h of t equals 51. Okay, that communicates to me what you're doing. And now we come in here, and instead of 53, we put 51. Now, we have to look for a very specific 51. It has to be 51 feet above the floor, moving away from the floor, which means it has to be going what? Up or down? Up. Do you see any points of intersection on here where they intersect going up? I see two of them, don't you? Does it matter which one we use? It doesn't matter which one we use, okay? Because it doesn't say going up for the first or second. It's just going up. So he can time it on any cycle that he wants. So I'm going to go ahead and find the first one. Second trace, number 5. Enter, enter. And let's see. I have to be at that point of intersection going up. The first one of which is this right here. Boom. Okay, so that's 2.75. So my new equation is going to take the original equation. I'll call it capital H of t. It's still going to be 10. It's still going to be cosine. It's still going to be 5 pi ninths. But now it's going to be t plus or minus the number 2.757. And then it's going to be plus 50. Now, again, my question to you is, if that needs to correspond now with my y-axis, do I move that graph left or right to make that the new y-axis? I got to pick that graph up and move it back to the left, which means in my equation, is this plus or minus? Good, it's plus. Okay. Now you could have also found the next one, which is going to be one period length away. The period is 3.6, so you could have added 3.6 to that and found the next one and shifted that to the right. Any of them would have worked. You could have even set your x-min to some negative number and found out where it was and then move it to the right if you want. However you want to do it, that needs to be your new y-axis, okay? Okay. So now we have a funky shift. So now, if that were the equation that we're using and I was asking you for how long it was above 9, the symmetry would be gone, right? So we'd have to actually find it the way I told you. So it's, but whatever. As long as you're thinking through the problems and you know what you're doing, that's the whole point of this lesson. You're not going to be doing sinusoids the rest of your life probably, but you're thinking, right? You're thinking critically and you're stretching your brain and you're coming up with these analytics that you can use the rest of your life for other situations. All right, little sister, she got involved. We're done. We're done with that one. There's only one more example left to go. We'll do it on Monday. And Monday, Fundy. Today's Friday, but Monday is Fundy. We're going to look at the Bay of Fundy, which is in Nova Scotia, and it has the highest tide differential in the world. Okay, twice a day the tide rolls in and rolls out, and the tide difference is 56 feet. That's incredible. Okay, it's incredible, and it actually happens. So we'll look at that on Monday. So make sure that you're working on your worksheet. Okay, make sure that you're beginning it. You don't want to do it all on Monday night because this will be due on Tuesday. All right. Any comments or questions? It's okay to get your siblings involved with your perpetual motion machines. We can fix it on the back end, can't we? Yeah, be nice.